Hello everyone, welcome back to Watchpoint. I'm Greg and we're going to look again at GDB and debugging multi-threaded programs. Now, a few episodes ago we had a guest lecturer, Shatabdi, who gave a very nice grounding on and base level of GDB use with threaded programs. We're going to build on that and look a little bit more how we can control which threads are running and see a bit more about how GDB and the operating system work together. So to do that, I've got a little demo program. Actually, this is almost the same program that we looked at last time. Let's get that up here. And so if you remember from last time, it basically the main thread just loops around, creates 4 worker threads, running this looper function, and each of these 4 threads just spins forever, and they all update. We have this 4-character array spinners, and each of the threads updates its entry in that array, just sort of spinning them around and around. The only difference from last time is I've added a few lines of code here to give each of my threads a name. We'll see that in just a moment. So GCC threads. So if I run it like this, okay, so here we are. There's the 4 worker threads. They're all busy spinning around, updating their entry in the spinners array, and that's printing out onto the screen like this. Okay, so let's run that in GDB. Run. Okay, here they all go. Control C. So now, when they appeared, note that GDB gave me this notification that these 4 new threads, the worker threads, have all arrived. And if I go info threads, of course, we can see them all here. So GDB, there's a couple of basics just to recap. So GDB has a notion of its own notions of thread IDs, 1, 2, 3, 4, 5. You can spot the pattern. But there's also the target ID. So this is what the operating system thinks of as the thread, and that's here. So we've got this pointer here is actually the pthread internal pointer, and then this thing LWP 189364. LWP stands for lightweight process. It comes, I believe, from Solaris or from that kind of generation of Unix, and that was the first kind of versions of threads that appeared. The early Unixes didn't have threads. Now in Linux, there isn't really a difference between threads and processes. In fact, processes are simply thread groups. So they all live in this process ID namespace. And so this is what the operating system will refer to that thread as. And you can see these are all unique, of course. And it also has this name. So a.out is the name of my program. And if I hadn't have set the name of each of the threads, then they would all have just inherited from the main thread a.out, but I set the name, so they've all got, I can see those names appearing here. So that's a little trick. You can set the name of your threads, and makes it a little bit easier from GDB to see what is doing what. We still have to refer to it from these thread IDs, but the mapping is pretty straightforward. So if I do a backtrace, or any command in GDB is going to apply to the selected thread, of course. So backtrace, so this is my thread 1, the first thread to exist, which is the main thread. And yeah, it's in this kind of somehow in pthread join. Don't backtrace doesn't make a huge amount of sense because stuff's been optimized, but we can kind of see what's going on there. And these other threads, I can see futex wait, and libc write. So these 3 threads are blocked on some kind of lock, and this thread is actually writing stuff to the screen. Now, when I continue, all of the threads continue running, including the main thread, but the main thread's not doing anything because it's blocked. It's kind of, all those threads are going to run forever, so none of those the pthread join in the main thread is never going to complete. Control C again. So, and I'm still in thread 1. All right. Now, it's a bit of fluke. I may have ended up in a different thread because it depends which thread receives the signal. So when I did Control C, my program receives SIGINT, and Linux is arranged for the main thread to be the one that receives a SIGINT. It's not actually defined. It could be any of the threads, but Linux seems to prefer the main thread here, so it stays in thread 1. If I go into thread 2, backtrace, and I can see that's obviously a different thread, not the main thread. Continue that. Control C. See, thread 1 has received the signal, so it's going to be back in thread. Is it going to be back in thread 1? Yes, it's back in thread 1 because that was the one to have received the signal. But if I don't receive a signal like that, then GDB is going to stay in whatever thread is selected. So if I type finish, remember finish will run the current stack frame until it returns in thread 1. Now, nothing's going to happen, right? Because that function is never going to return because the pthread join is never going to complete. In fact, Control C, if I step I, this is the smallest movement you can do in GDB, right? Stepping one single instruction. It doesn't even do that because that thread is blocked inside that pthread join system call, so I can't even move forward one instruction. Okay, makes sense, right? So when I type step I, it's going to run all of the threads in my program, even if there are hundreds or thousands. They're all going to get run, and then it's going to step I that one instruction, that one thread if it can. So let's go to thread 5. So that is inside. They're all kind of inside system calls because this program is actually going to spend most of its time inside system calls. And so now when I step I, I've printed some stuff onto the screen. Thread. Oh, I don't know why that happens. Ignore that. Step I. That's a bug, I think, in the system. I shouldn't have received that SIGINT, but so it's going to stay inside thread 5 now as I step I, but other threads are going to be allowed to make progress. If I show that spinners, well, let's finish up actually. Let's get back into our own code. So let's go into 2 mode so we can see what's going on. So finish, keep going. Okay, so now I'm in our code that we wrote, and if I display the array spinners, and now I do a next. So which thread are we? I can probably determine now. We're in thread 5, the 4th worker thread, this 4th entry on spinners, and it's not moving, but all of the other threads are updating, and like a lot, right? They're all getting a lot of work done. Even if I step I, just to step one single instruction of this 5th thread, look, every single one of these threads moved its spinners on, like at least one. In fact, I suspect a lot of them just wrapped around. I mean, it's a lot happens in the time it does that step I, because it's step I, it runs thread 5 one instruction. All the other threads, it just completely starts them and lets them run free. And then when thread 5 stops, it's going to just stop all of the other threads and bring them to a halt. So lots happening in the background, even though I'm only stepping one instruction in that thread. Now that's usually kind of what I want to happen, but it may not be. It may be confusing. It may be unhelpful as in this case here, I've got multiple threads operating on this data structure. Now this is a very simple data structure. It's an array of 4 characters, but maybe it's more complex. And I'm trying to see what my thread is doing. And every time I step it forward or run it to a breakpoint or whatever, all these other threads are running and messing everything up and moving the world like underneath my feet. Maybe I don't want that. So if I don't want that, I can set scheduler locking on. And now when I type next, so look, this one has moved forward 1 because it just incremented its entry in spinners. Next, next, next. It's not updating these others, but now it's got stuck. Now, why has that happened? Well, Control C. Let's come out of 2 mode for a moment because I want to use more screen real estate to show you what's going on. Info threads. So that's the thread I was stepping, and it's stopped at this lock. And look, this other thread number 2, it's inside libc right. So what's happened here is libc has a sort of internal global lock, and when I was doing next before I'd done the set scheduler locking on, thread 2 had grabbed that lock, and now it's got it, right? And so now when my thread that I'm stepping gets into libc, needs to take that lock, everything deadlocks. That's the problem with set scheduler locking on. My next, it's deadlocked because this only thread 5 is running, and thread 2 has the lock that thread 5 is trying to get. So if I set scheduler locking, leave scheduler locking on and set my thread to number 2, now I can run that. Let's just continue it, and we can see that that's running away. And so that's the thing with set scheduler locking on. I mean, be careful, and that's why it's not the default, because you can quite easily get these deadlock situations, even if you don't think you've got any locks. libc has locks, and you're likely to trip over them. But if I know what I'm doing and I don't want any other threads to run, set scheduler locking can be very useful. Or I can go set scheduler locking step. Now what this will do, when I step, it will leave the locking on, so nothing else was running there. But if I continue, it will run all of the threads. If let's just, I want to come out of, I'm going back into TUI mode now, and if I come out of this, I just want to show you a bit more, so this might become clear, just in case it wasn't clear. So info threads, so which threads do we think have that? I think it's number 3, because that's inside the write function. So switch to thread 3, finish a few times. I want to get into our code, out of libc. Here, right. Okay, so that's what I wanted. I just wanted to actually see what line. So line 17. So if I put a break on line 17, set show. I think I'm in stepping mode, right? Yeah, step. So now I continue. So now all of my threads will have run until they hit this breakpoint. Now it's not guaranteed that all threads will get to the breakpoint, but in practice they usually will here, and they have here. I might need to continue a few times just to get every thread up to that breakpoint. So now all my threads are in my code. None of the threads have those pesky libc locks. So let's just delete that breakpoint, and I'm going to set schedule locking mode on, and now continue, and you can see just that thread. The screen is messed up a bit there, but just that thread is running. If I put that break back on threads.c line 17, and now I can thread 5 disable this time, disable that breakpoint, continue. See, just that thread runs. So continue to determine which thread runs, and if I know what I'm doing, that can be a more useful, helpful way to debug my multi-threaded program. I do hear people say, by the way, that GDB is not very good for debugging multi-threaded programs. Never really understood that point. I think this might be part of what people get upset by. I think if you don't really understand what the operating system is doing with threads, what by operating system I'm including like libc and other system libraries, and you don't really understand about how GDB is starting and stopping all the threads in lockstep unless you unless you tell it not to, then I think it can get very confusing and very unhelpful. Once you understand this stuff, I think GDB is perfectly capable of debugging very threaded programs, and in fact it's threaded programs that give us some of the worst kinds of bugs, so very good that it is too. Thank you for listening and paying attention, and I'll see you next time.